In this video we present our augmented crowd simulation system using automatic determination of navigable areas. Our augmented crowd simulation framework consists of 4 subsystems. First, we pre-process our input, surveillance-alike static video. We detect and track the pedestrians in it, which will be used for navigable region calculation, scene reconstruction, and crowd simulation. We calculate the navigable regions of the scene using semantic segmentation of the input video and the pedestrian data. We reconstruct the navigable regions as a 2D navigation mesh, to be placed in our 3D simulation environment. We also estimate the camera configuration of the scene. Finally, we position the 2D navigation mesh into the 3D simulation environment in Unity, along with the input video, pedestrian data, and the camera calibration. We then integrate artificial agents into our crowd simulation using collision avoidance algorithms. Now, we will briefly explain each subsystem in order. We first detect and track the real pedestrians in the scene. The dynamic pedestrians in the video are detected and tracked using various methods including deep learning and Kalman filters. Static pedestrians are ignored, only regions where a motion occurs are searched. We use the pedestrian location and posture information for navigable region calculation, scene reconstruction, and crowd simulation. Then, using semantic segmentation methods, we determine the navigable regions in the video. We accumulate the segmentation results to synthesize the navigable region candidates, filtering out the obvious impassable regions such as walls. Then we integrate the pedestrian locations, and determine the navigability of each region based the ratio of the occupying pedestrians. We compose a binary image with the union of the regions based on navigability, where white indicates navigable. In this image we overlay the impassable regions on top of an example frame. In case of realism, it is better to lose a possible navigable area due to bad segmentation than to have pedestrians fly over non-navigable regions. Using the first frame of the video, pedestrian navigation data, we estimate the camera calibration in the scene and reconstruct the navigable regions mesh. For camera calibration, we use image lines from the first frame, as well as pedestrian postures and trajectories. Pedestrian trajectories meet at the horizon, and pedestrian postures converge at the third vanishing point. Using the vanishing points of the scene, we apply stratified rectification to prospectively correct our image and obtain the blueprint of our navigable area. The blueprint can be considered as top-down map of our navigable regions. In order to get an initial camera configuration, we use perspective endpoint solvers. However, the initial solution of perspective correction is erroneous because of distortions and focal length errors. For perfect placement of the model in the simulation, the model corners projection should match the image corners. We propose a method to solve this placement problem. We don't have the depth information. However, the projection matrix is the inverse of a matrix that would map image points to 3D world coordinates. Therefore, as we know that the navigable area sits on XZ plane in Unity, we remove its Y component. This turns the problem into a plane-to-plane homography. We obtain the projection from 4-point correspondences. Corners of image and the model are in their respective spaces. We reverse the projection to project image points over XZ plane. Then we calculate another adjustment homography for perfect model. After readjusting the model, we obtain a perfect placement according to image corners. Here is our corrected model that is ready for placement. Here, we show a comparison between initial navigable region image and its perspective corrected correspondence. We convert the final version of the navigable region into a 3D model using triangulation techniques. Now, the model's mesh is ready to be imported into Unity. Here we show an example placement of the navigable region into our simulation. Navigation mesh is visualized with black in this image. Finally, after placing the navigable region model in Unity, we can project the pedestrians from the real video and simulate them together with user-controlled artificial agents. We project the pedestrians by sending a ray from camera to navigable mesh. The height of all agents in the simulation is determined by the average height of the detection boxes in the 3D scene. The 3D camera looks at the navigation mesh, so that it overlaps with the navigable regions of the input video. We place dummy agents, visualized with green, in place of the real pedestrians, to be used in collision avoidance. We provide an extensive user interface to the user to add and control the artificial agents in the video. Virtual agents, shown in yellow, avoid the green dummy agents while walking towards user-defined destinations. In our simulation environment, the user can view the reconstructed navigation mesh and the dummy agents on top of the input video. The user can insert virtual agents into the scene, and click on the navigation mesh to assign a destination for the selected agents. Selected agents are highlighted with yellow. We select all virtual agents for a period in the following examples for ease of recognition. Currently we render all virtual agents in front of the input video, therefore pedestrians cannot overlap the virtual crowd even if the pedestrian is in front of the virtual agent in the 3D simulation environment. Now, we will show some augmented crowd simulation examples.